So we have started with a technique known as ANOVA, or analysis of variance. And despite what the name suggests, this is still a statistical method that compares population averages to one another. Now, ANOVA is specifically designed for when you have multiple populations. If you only have two populations you're comparing, you should fall back on the t-test or the z-test methodology for two samples. You can use ANOVA in those instances, but it's a little bit overkill to try and use ANOVA in those instances, although it will give you at the end of the day the exact same conclusion as the t-test with equal variances assumed. So ANOVA assumes you have multiple populations or multiple treatment groups, each one drawn from a normal population. So starting assumption is normality. All the populations are allowed to have different means, but we assume a common variance. And so that's why if you're comparing it to a t-test scenario in the two sample case, it has to be where we're pooling variances. So let's look at this first example. Here we have the results from an experiment where a total of 16 units were randomly assigned to one of four possible treatments. So our number of groups is 4, and J would be the number of observations per group, which in this case is also 4. Now, the table summarizes, you'll see it has the raw data, what the actual measurements are for each of the treatments, and then it also has the summary information. So for each treatment, both the average and the variance within that treatment group. And as long as you have the means and the variances, you really don't need to do anything with the raw data. So that's kind of more information than you really need in this instance. You're only concerned with those summary measures. So first question asks us to formulate the null and the alternative hypotheses for a single factor ANOVA. And single factor ANOVA is the only kind of ANOVA that we'll be doing. That just means we're not, say, trying to compare both a treatment and a dose within the treatment. Like that, there aren't two different factors that we're comparing. There's just a treatment that's different across groups. If that's kind of clear. If you add extra layers to it, it's no longer a single factor ANOVA, but that's beyond what we'll be covering in this class. So our null hypothesis is that all the treatment populations have equal means. So this would be mu1 equals mu2 equals mu3 equals mu4. All the treatment means are equal. And the only variation of an alternative that we have is that at least two means are different. So an alternative way that you could express that is you could say mu I not equal to mu j for some pair I and j. That's just saying you can go and find two groups with different means. So that's what our null and our alternative hypotheses look like. Next, we're asked to calculate the mean squares of treatment and the mean square error. Now, let's in this first example actually go to the trouble of just fully writing out these formulas so that we're all on the same page. Mean square of treatment is defined as J over I minus 1, and then it'll be each group average minus the overall average squared, and you do that for each of the groups. And just a question here about the alternative. You do have to, if you're writing it in mathematical terms, you do have to say for some I and j. That's how it will generally be formulated. So we have our mean square treatment formula here. We can plug in our specific values in this instance. So we know j is 4, I is also 4, so I minus 1 is 3. And now we're taking each group average, and we have to subtract the global average from that. So we need to find the global average. Now again, if you're working with the raw data, you'll sum all of the raw data values together and divide by 16. But since we already have the group averages, we can just sum those together and divide by 4. And if you go and do that here, you will get 20.985. So that's the overall average in the comprehensive data set. So you'll take each group average, subtract the overall average from it, and you just do that for each of the 4 groups in this instance. So unfortunately, ANOVA is a bit tedious calculation-wise. There's no shortcut here to doing this calculation. But if you go and evaluate this, you will get 13.412. Then we need mean square error. This formula is the equivalent of how we pooled information in the variance formula for the 2-sample t-test, except there's no weighting because the group sizes are all equal. So we're just adding the individual group variances and dividing by how many of those we have. And so our mean squares of error is 18.943. Okay, so that now allows us to calculate the value of F observed. Now, F observed is just the ratio mean square of treatment over mean square of error. Which in this case is 0.708. So now we need to use an F distribution as a reference for calculating the p-value, and that requires evaluating 2 different degree of freedom numbers. Numerator degrees of freedom, which is I minus 1, which in this case is 3, denominator degrees of freedom, which is I times j minus 1. So in this case, 4 times 3 or 12. And so we are using an F distribution with 3 and 12 degrees of freedom as a reference. So if we picture this, we have this strictly positive skew distribution. We have a value 0.708, and our p-value for an ANOVA is always the exceedance or the tail probability. So we want to know what the total area in the tail tail is, that's our p-value. Now, on your TI-84 or your Inspire, you have a function called FCDF. And the way I recommend using it is it'll ask you for a lower bound and an upper bound. And I recommend using lower bound as 0 and upper bound your observed statistic. Technically, you could go and put in this case, the 0.708 as a lower bound and make the upper bound arbitrarily large. But depending on the degrees of freedom, you can run into difficulties for what you put in as a large number, because depending on the degrees of freedom, what large means will change. So it's easier calculating the area to the left because 0 is 0. You don't have to worry about whether you're entering a large enough value. And then 2 degrees of freedom values, the new one first and the new 2 second. And if you go and plug this in on your calculator, this will give you, in this instance, 0.435. So your p-value is just 1 minus the probability you've calculated. And that is 0.565. Now, if anyone does not have a TI-84 or an Inspire, just reach out to me. There is a table you can use for these F calculations, but I suspect most of you have the calculators you need for this. But let me know if you don't. So last part of the question says, state your conclusion at the 5% level of significance. So our p-value is definitely larger than our alpha of 0.05. So we do not reject the null hypothesis. And what that means in this instance is the sample evidence is consistent with all the treatments being equivalent on average. And you have to write that kind of statement. I'm just running out of space here. I'll try and cram it in here. So sample evidence is consistent with all treatment averages being equal. So at least on average, we don't see any evidence that there is a difference between these 4 treatments. And I think at this point, you kind of have the rhythm of interpreting a p-value and writing down a conclusion. But I will emphasize that's one of the biggest point killers that we had on this most recent test. Many of you would stop at reject or do not reject the null hypothesis and not actually write what that tells you in the context of the problem. And you lost, each time you did that, 2 or 3 points, depending on the severity of how badly you missed the mark there. But hopefully beyond that, the ANOVA, all that's new is different formulas and plugging numbers into those formulas. Does anyone have a question about this first example problem? So second example is going to be very similar. So it'll give you more of a feel for how this all plays out. In this case, you'll see I didn't put in the raw data. I just gave group means, group standard deviation. So we're looking at an experiment where 50 zirconium oxide discs were randomly divided into 5 groups, 5 different treatments, each consisting of 10 observations. A different contamination and cleaning protocol was used for each group, and we measured shear bond strength associated with the different treatments. So we want to do an ANOVA to evaluate whether on average the treatments result in a different average shear bond strength. So null hypothesis will be mu1 equals mu2. And depending on how many groups you have, I'm totally okay with you using like an ellipse in the middle as long as you indicate you're evaluating equality across all the groups. So you have first and last group at least. And your alternative will be mu I not equal to mu j for some pair ij. Next, we want to calculate mean square of treatment and mean square error. So again, this requires calculating the overall average first. So you'll sum all your group averages, divide by how many groups there are. And in this case, the group average is 15.72. Now we can calculate mean square of treatment, j over I minus 1. So in this case, 10 over 4. And now it will be each group average minus the overall average. And I know I talked about this in the lecture on YouTube, but the intuition about what's happening with mean square of treatment is you're looking at how far each group average is from the overall average. And if all the group averages are the same, then all of these square differences should be small numbers. If there are groups that are substantially different, then some of these square differences will be large. Now, ultimately, F observed and the p-value determines what is considered small or what is considered large, but that's the intuition here. If the differences are small, then the groups are the same on average. If we find large deviations between a specific group and the overall average, that's evidence that there is a difference between the treatments. So in this case, if we evaluate mean square of treatment, you will get 156.87. Mean square of error is the average of the variances. So here you just want to be careful because you're given standard deviations and you need to average the variances. So you want to square them. And if we evaluate that, we get 37.926. So this gives us what we need to calculate our F observed statistic. And that is 4.136. So if we want the p-value, we need to know degrees of freedom. In this case, I minus 1 is 4, and I times j minus 1 is 45. So we'll use an F distribution with 4 and 45 degrees of freedom as a reference. And so our p-value will be 1 minus, if I do my FCDF again, lower bound of 0, upper bound of 4.136, and I have my 2 degree of freedom values. That FCDF is 0.994, and so our p-value is 0.006. So in this instance, we're trying to reach a conclusion at the 1% level of significance. So our p-value is less than the alpha, which means we reject the null hypothesis. In other words, what we can say is that there are treatments with different average bond strengths. Or, I mean, more correct, I should say, sample evidence is consistent with. We don't want to make too definitive a statement because we're always still keeping in mind if we are not rejecting the null hypothesis, we could still be making a type 1 error. If we are rejecting the null hypothesis, we could be making a type 2 error. Those are always possibilities. So we do reject the null hypothesis here. Most likely, there are differences in the treatments. But what we'll get to on Thursday is we're saying we're finding a difference, but where is that difference now? Are all the treatments different from one another? Is there only one treatment that's radically different from the rest? We don't have the ability to make a more definitive claim about which treatments actually differ from which other treatments just based on what we've done here. So what we'll look at on Thursday is something called a post hoc analysis, where we dig a little deeper to now figure out which of the treatments are the same, which of the treatments appear to be different from one another. Because just scanning the treatment averages, the most we can say is, since there is evidence of a difference, definitely the lowest treatment average and the highest treatment average are going to be different from one another. But what about the lowest and the next highest? Like, we don't know. That's what we'll have to go and investigate. Any questions about this example before I move on? So last example for today just has to do with how the mean square and sum of square quantities are related to one another, and what often the expectation is around how all of these results get reported. Because in different fields, people attach value to different summary measures of the data. So from a statistical perspective, we give them a comprehensive summary so that people can pick out what they want to look at and what they consider important. And that just means we want to summarize everything in what we call a sum of squares table, which you see a partially completed one in front of you. So here we have summary measures for an experiment that was carried out to compare the electrical resistivity for 6 different low permeability concrete bridge deck mixtures. Say that fast 5 times. So we have 6 different treatments that we're comparing, and there were 26 observations for each treatment. And these were obtained 20 days after casting. That's not relevant to this table. We want to complete the ANOVA table below, state the null and alternative hypotheses, and state our conclusion at the 3% level of significance. So our null hypothesis is that all the treatments have equal means. Our alternative is that there's at least one pair where the treatment means are different. And now we want to go and complete this sum of squares table. I'm going to zoom in here a little bit so that I can just write on the table. So easy information always is just filling out the degrees of freedom. Mixture, which is our treatment degrees of freedom will always be I minus 1. Error degrees of freedom will always be I times j minus 1. And you can just sum those to get total degrees of freedom. But you can also calculate total degrees of freedom as I times j minus 1. So if I fill these out, since I have 6 treatments, 5 treatment degrees of freedom. I times j minus 1 in this case for error gives me 150, which means total degrees of freedom 155. And this should always be total sample size minus 1. So the relationship between mean square and sum of squares is always you get the mean squares by taking the sum of squares divided by the degrees of freedom. So since we have mean square of error, we can get back to the sum of squares just by multiplying by the degrees of freedom, which in this case will give us 2089.35. And now it's worth remembering, sum of squares total is equal to sum of squares treatment plus sum of squares error. So again, there's this 2 of the quantity summed to the third. And since we know sum of squares for the total, we can subtract sum of squares error to get sum of squares treatment, which in this case is 3575.065. And now we can convert that to a mean square value just by dividing by the degrees of freedom, which is 5. So if we do that here, we get 715.013. And that gives us everything we need to calculate F observed, because F observed is just the ratio of the treatment mean squares divided by the error mean squares, which in this case is 51.333. So there is my completed sum of squares table. That is how all of those quantities connect together and relate to one another. Let's see a question here. So I had a question just about the sum of squares error again. The sum of squares and the mean squares are related to one another in that if you take the sum of squares and you divide by the degrees of freedom, you'll get mean squares. So that means I can recover sum of squares from mean squares by multiplying with the degrees of freedom. So that's what I did here. I took the mean square, I multiplied by the degrees of freedom, and that's how I recovered the sum of square entry for error in this instance. So we have our F observed, which means we can calculate our p-value using the appropriate reference distribution. Now here, the distribution degrees of freedom also just, you'll see the formulas here. Sorry about that. The formulas here are exactly the degrees of freedom formulas for the reference distribution. So you can just pick them out of the table if you've constructed it. So we'll use an F distribution with 5 and 150 degrees of freedom. And so our p-value will be 1 minus the FCDF, lower bound of 0, upper bound 51.333, numerator degrees of freedom 5, denominator degrees of freedom 150. And if you go through this calculation, We'll see you get a pretty small p-value. So our p-value in this case of 0.0002 is less than our alpha of 3%. So again, in this case, we reject our null hypothesis. So the sample evidence suggests there are at least some treatment groups that differ from other treatment groups on average. But we will have to dig a little deeper to figure out where those differences are. And another question just about F observed. F observed is defined as mean square of treatment divided by mean square of error. So I have mean square of treatment and mean square of error in the table. So F observed is just the ratio of those two numbers. There'll definitely be an example comparable to this one on the homework. So it'll give you another opportunity to develop a feel for structuring this table and all the different components.